So we've talked a little bit about this. What would the square root function probably look like? Eric. Okay, like a sideways quadratic. Now remember when you guys were solving for the inverses of the quadratic? No, right now you should do this on a note. There was a note guide that I gave you guys too. We will put it in your blue thing, yeah, like there, that you could print out that had all the graphing stuff on it. So if not, just put it in notes. So when you guys took the inverse of a quadratic, you got this kind of sideways parabola and it had a square root in it. Right? But those ones, when you guys took the inverses, you square rooted both sides of the equation, so your square root function had a plus or minus in front of it. So you were actually graphing two square root functions at the same time because of the plus and the minus. So the square root function that just has the square root of x, and we talked about this, if you plug in a number for x right now, and you calculate the square root, do you expect a positive or a negative result? Positive. Only by putting the minus in front would you get a negative result. Right? And what kind of numbers can we put in for x if we want to get real number answers? Positives. If we plug negatives in, it would give us imaginaries, right? So the parent function for the square root only exists in quadrant 1 because to calculate a square root, we can only plug in positive x values. And then since there's no negative in front of the square root, we only expect positive y values as the outcome. So if we plug in 0, the square root of 0 is 0. If we plug in 1, the square root of 1 is 1. And if we plug in 4, the square root of 4 is 2. So we get this curve. It does not flatten out. It does keep growing, but it just grows very slowly. How far out would we have to be on the x-axis for this function to finally reach a height of 10? 100. You'd have to be all the way out at 100 before you'd reach 10 because of the way the square root function works. Okay? So this is a new shape. We do have to know this new shape. But the transformations with this shape should all be familiar to us, so we're kind of reviewing that idea and then doing those transformations with this shape. So we should now be able to answer these things. What is the x-intercept of the graph? 0, 0. And the y-intercept? 0, 0. Okay, and we talked a little bit about this just now. We just didn't call it domain and range. What is the domain of this function? Helen? Good. X would be greater than or equal to 0. What about the range of the function? Eric? All real numbers? But same thing we talked about before. Without a negative in front of here, can you really get a negative value once you calculate the square root? No, actually. So y is also greater than or equal to 0. Now, obviously, this will change if we shift the graph left or right or reflect it so that it faces another way. Okay? But you kind of always have this like arrow shooting off of some end point. And so when we ask for the vertex point, even though this isn't really a turning around point, we're referring to that 0, 0. Always the place of the parent function that starts at that 0, 0 for these graphs. Okay? All right. Are we all good with this information? Any objections to changing it? All right, so here we have f of x equals 3 times the square root of x minus 1 plus 2. So the only thing that we've changed is instead of having a set of parentheses with a little squared outside of it or absolute value bars, now all the inside stuff of our function is happening underneath the radical because we're using a square root function. So who thinks they remember how these transformations work and can tell me what one of the transformations is that's going to occur from the parent function? Cody. Good. So the minus 1 is going to shift us 1 to the right. What else? Sean. Or, sorry, I saw Sean's hand last time. Raven. Okay, good. So we're going to move to the right one. We're going to move up 2. And what else is going to happen? Alex. A vertical stretch by 3. Okay, cool. So I'm going to make sure I put all that stuff here. So we're going to move to the right one. That's a shift or a translation. We're going to vertically stretch, and that was that factor of 3. And we're going to shift up 2. Where is the new vertex of my graph then going to end up? Any ideas? Instead of that starting point being 0, 0, where do you think it's going to be now? No. So remember that what the 3 is going to do, it does stretch it. So you're thinking the right thing, except for it stretches everything from the vertex. So the stretch doesn't change where the vertex is. It just stretches things around the vertex. Jordan. Good. It's going to move to 1, 2, because 1 is going to be our new x coordinate because we basically picked up the graph and moved it over 1 to the right, and then we moved it up 2. So whether you like doing the vertex point at the beginning or the end, we should be able to identify that as our starting point. Okay? Now, once you've identified that starting point, you've actually already taken care of this and this. Okay? I don't know what's doing that. The only other thing is that a vertical stretch by 3 is happening. So normally, from our parent function, this would be the point at 0, 0, and then there was a point that was over 1 and up 1, and then there was another point that was over 4 and up 2. So that would be the normal parent graph just shifted over 1 and up 2. But now we have to account for the vertical stretch. How is the vertical stretch going to affect the points that are up here? Eric? Okay, it's going to multiply whatever I went up by 3. And so when we were measuring these points, we were just kind of measuring away from the vertex point, how far they were horizontally and then vertically. The vertical stretch is not going to change the horizontal distance. So this point is still going to be 1 point away from the vertex horizontally. However, it was vertically 1 unit away from the vertex. That was their distance. What will their distance be now that we have a multiplier of 3? 3. Okay, we literally are going to take 1, multiply it by 3. 1 times 3 is 3, which means I don't want that point to be 1 unit above the vertex anymore. I want it to be 3 units above the vertex. Okay. This other point out here that we were using as a reference point, it was vertically 2 units, okay, above the vertex point. How far above the vertex point do we want it to be after we've applied our stretch of 3? 6. So 1, 2, 3, 4, 5, 6. It'd be somewhere way up there off my graph. Okay. So my new graph would go like this. Okay. It doesn't look like it grows as slow. That's because it's been stretched out vertically. Any questions about that? Are we remembering the transformations? Okay. They haven't changed. It's just the shape and structure of our parent graph that has changed, but we're applying all the same things to them. Any objections to changing this? Actually, let's also list the domain and the range for it so that we're familiar. What would be the domain of this function? Helen? Good. Do you guys see why it changed to x is greater than or equal to 1 instead of 0 like it was with the parent function? Okay, our whole graph got shifted to the right one. So now the x values are only valid from here over. And you can see that graphically. You can also think about it algebraically. Look at the equation. Why does it make sense that 1 is the smallest x value that I can plug into the equation, and I'm not allowed to plug in anything below it? Julia? Good. If I plug in anything smaller than 1, and then I subtract 1 from it, I'm going to get a negative underneath the radical, and I'm not going to be able to finish a real number calculation in my algebra problem. So we can see the domain and range from the equation and also from the graph. It's just sometimes a lot easier from the picture than it is to think about all the possibilities in the equation. What about the range of the graph? Raven? Do you guys see why it's y is greater than or equal to 2? Okay, that the whole graph was shifted up 2 units. Okay? And algebraically, you can see that because what's the smallest value we're going to get for our square root if 1 is the smallest x value that you can plug in? Once you calculate the square root, what's the smallest number it could end up being? So this just that square root of x minus 1 part. Once I plug in an x and I calculate the square root, what's the smallest number I can get for that part of the equation? 0, right? I can't get anything smaller, right? Because I can't get a negative or anything like that. If the square root part of the equation, if the smallest thing that it can be is 0, think about putting a 0 right there. 3 times 0 would be 0. So all the part attached to the square root, the smallest it can be is 0. But then at the end, we're going and we're adding 2. So overall, the smallest calculation you can get for the entire equation is 2, because that part can become 0, but you're always going to be adding 2 onto it at the end. So that's how we could see the range algebraically, but obviously it's much easier to see it graphically that the whole thing was shifted up to. All right, for this one, okay, notice there's a lot more going on inside the radical, which means what kind of transformations are happening here? Horizontal, because a bunch of stuff is happening in the radical. So think about factoring what's in the radical so we can see this a little more clearly. If I factor out a negative 2, I'm left with x minus 2. I do that because it helps me see what the true shifts and different things are. So help me list the transformations. What do we see here? Helen? Good. A horizontal compression because of the 2 that's multiplying there, which basically means horizontally everything gets multiplied by the reciprocal of 2, which is 1/2. Matt? Good. So a horizontal reflection, which means it's going across the y-axis, so it's going from left to right, right to left. Okay. Julia? Okay, good. And we have this shift right 2. Now, if we're going to graph, I do know something. Because the shift is right 2, I know that I expect the vertex to end up at 2, 0. Okay? But here's one thing you want to avoid doing. You don't want to put the vertex and then go and do your horizontal reflection, because now if you reflect horizontally, where does this end up? Negative 2, 0, but is your vertex supposed to be at negative 2, 0? It's supposed to be at 2, 0. So either you understand that if you did this first, it's just going to shift the arrow from going towards the right to going towards the left, and you just measure from there, then that's fine. Or you need to go through the reflections more carefully, and you need to start with the horizontal reflection if you're going to do it piece by piece. Okay? So remember, when we reflect, our vertex isn't going to change its location. Normally, the parent function went over 1 and had a point 1 above, okay, towards the right. But now with our horizontal reflection, that point is no longer going to be there. It's going to be over here. Okay? And then the other point we used for reference was over 4 up 2 on that side. But now it's going to be on the other side. So this is what just the horizontal reflection part would look like. So we'd be done if we were just graphing the square root of negative x. Okay? It'd be done. But then we have to account for all of these other things. We have to shift and we have to compress our graph horizontally. So let's say we compress our graph horizontally by 1/2. What does that mean I'm going to do? Good. But this time instead of up and down, it's just a cross because it's horizontal. So these points here were 1 unit apart. But I'm going to use this multiplier to calculate the new distance they should be apart horizontally. So if I take 1 and I multiply it by 1/2, I get 1/2. The height of this point is not going to change, but instead of it being 1 full unit away from the vertex, it should only be 1/2 a unit away. In other words, it should be here. Okay? What about the distance between the vertex and the other point that we're using for reference? How far apart are they? So vertex horizontally over to this other point that we plotted. How many units? 1, 2, 3, 4. Okay. And then we're compressing. Again, that means multiplying in this case by 1/2. And 4 times 1/2 is going to be 2. Okay? That means instead of these points being 4 units apart, the height of this point is not going to change because I have no vertical change going on here. I just want it to only be 2 units away from the vertex instead of 4. So this point is now going to be plotted here. Okay? So at that point, it looks like this. So it looks a little bit like a vertical stretch, but that makes sense because compressing something horizontally kind of does the same thing as stretching it vertically, but with different number values. Then the last thing we have to do is shift it to the right too. So instead of our vertex being here at 0, 0, it'll be here at 2, 0. Instead of there being a point 1 over horizontally and 1 up, it'll be half over horizontally and 1 up. And instead of 4 over horizontally and 2 up, it's 2 over horizontally and 2 up. So that's how we'll get our final graph. All right, what is the domain of our function? Helen? X is less than or equal to positive 2. Good. And notice this time it's x is less than or equal to because of that horizontal reflection. Okay, somebody new. What about our range? Yeah, Jay. Good. Y is greater than or equal to 0. We didn't shift anything up or down or reflect vertically, so it kind of stayed with that same range that we had from our parent function. Okay. Any objections to changing this? Yeah, Alex. So we had a horizontal reflection. So graphically, here's why. Here's our point, right? On our x-axis, we don't have anything to the right of it. Our whole graph consists of points to the left of that. So that's what it would be graphically. The reason it turned out that way algebraically is if you look at the equation, and maybe it helps to look at this version right here. If we cannot have a negative underneath the radical, this part is already negative. So in order to be able to finish the calculation, I need this part to be negative also, right? And so in order for this to be negative, I would have to plug in a number for x that is less than 2. Otherwise, it would turn out to be positive, and the positive times a negative would make a negative under the radical. Okay? All right, last one for us to look at today. All right, so list for me transformations. So new people, okay? List for us some transformations. Pick one out. Get yours done quick. Jordan. Good. Okay, so there's a vertical compression because of that 1/2 that's there. All right. Did he take yours, Addie? Yes? Bailey. Good. There's a vertical shift here that moves the graph down 3. Shannon. Good. And a reflection over the x-axis. Okay, some sort of up-down type of reflection, so vertical, which means over the x-axis. And you don't have to say vertical. If you said over the x-axis, that's fine. You need to say one of them, and it has to match up with what it is. All right, so again, if we're going to do this with our reflection, if I start from the beginning, remember my parent function kind of followed those value of points. There is no horizontal changes, so I can go straight to the vertical changes, and I kind of want to reflect before I do anything else. If you know these well enough, you know that that's not actually true. There are some things you can do before you reflect, but you generally have to reflect horizontally or vertically before you shift horizontally or vertically, or you'll end up kind of in the wrong place. So we'll just go through and follow them that way, starting with reflections. So we'll go ahead and reflect vertically, which means we keep our vertex point where it is, and then these points just flip over the x-axis. So they are giving us this kind of downward going arrow instead of upward curve. Okay. Then we're going to vertically compress by 1/2. So just like last time, we're looking at the current distance any point is from the vertex and timesing it by 1/2. But this time we're looking at vertical distance. So like for this point right here, the vertical distance is 1. I'm going to times that by 1/2, which is going to give me 1/2. So I want that point to stay in the same position horizontally. I don't want it to move at all left or right. But instead of being 1 unit away from the vertex, so 1 unit below, I only want it to be 1/2 unit below. Okay, so same direction but less distance. So I'm going to go ahead and replot that point 1/2 unit below the vertex. So what about for this point out here? Currently, how many units is it vertically away from the vertex? 2. Okay. The level of the vertex is here. The level of that point is there for a distance of 2. If we compress that by 1/2, in other words, we take 2, we multiply it by 1/2, then our result becomes what? 1. That means we only want this point to be 1 unit away from the vertex in its vertical distance, so we should place it here. Okay? So this curve here would be us vertically compressing by 1/2. And then the last thing we would do is we want to move the entire graph down 3. So instead of our vertex being at 0, 0, it's going to be at 0, -3. And instead of our points being over 1, down 1, they're over 1, only down 1/2, and over 4, only down 1 instead of 2. So we get that curve there. Okay. All right, domain. So again, new people. Domain and range. So domain x values, Bailey. Good. Okay, and again, graphically, we can see that the whole graph exists with x values 0 or more. And algebraically, you can see that since it's just x inside the radical, you'll be successful in doing a calculation as long as you plug in 0 or a positive number. Julia? Good. So y is less than or equal to -3. Okay. Again, we can see that here because we can see that the whole graph goes below that point, which is at -3. How you would know that by looking at the equation is the shift of -3. And the reason, how would you know it's below that -3 and not above the -3? Just by looking at the equation. Helen? Good. So when I see the -3, I know the whole graph is getting shifted down 3, so I probably knew the range had something to do with -3. But our parent function goes up, so some people might think above -3. But the fact that the equation started with a negative number, which vertically reflected, that's how we would know it would go below -3 instead of above. Okay? Any questions?